A very good morning to everybody, and it's nice to be here second time in a row because I think last time I was here last year and I spoke on thermal management. So, and this time again I'm going to speak on thermal management, but people who have some glimpses of my last year's speech, which I think the organizers have put in the YouTube channel, so you can still. So I'm going to talk about something slightly different, but in the domain of thermal management. I think as Lavanya has introduced me, my name is Rajeev Kumria, and I'm Managing Director of H.E.L India Private Limited. This is a company which is one of the largest manufacturers and suppliers, and probably among the few companies which is making products for battery testing in thermal management domain. So we are basically a chemical engineering company into calorimetry, and some of those concepts we have taken over to battery management also. So I'll be mindful of the time, as Mr. Shiva has told me. So I think, we see that batteries are everywhere, from our electric toothbrushes to the EV, the cars that we drive, the laptops that we use, the mobile phones, which we always have. So, batteries are closer to us than anything else. But as battery adoption in each and every device increases, there is a need for higher energy density, there is a need for higher current, for faster charging, and of course, as the expanse of battery usage increases, like EV, more mileage, more range, you require larger battery packs. So there is a flip side to all of these, that the higher energy density batteries are more thermally unstable. Higher current means more instability and shorter lifespan of battery, which also nobody wants because it increases the cost of ownership of the device. And larger packs means larger hazards. So just, don't get daunted by these graphs and all because, we are a science and tech company. We love our graphs and numbers, but don't get daunted. It's just an illustration of what exactly happens when we are using battery in any device, and especially EVs. So there is an optimum zone of, it doesn't work. There is an optimum zone of performance of the battery where the battery will give you maximal life. Not optimal, but maximal life and maximal performance. And then there is a second zone called safe zone, in which the battery will provide you good life and good performance within the safety realms. But when the battery breaches these two zones, it gets into a zone which is a dangerous zone. And any type of thermal hazard or any hazard can happen in this particular zone. So as adopters of battery, as consumers of battery, as developers of products like the EV, where large battery packs are used, we have to be mindful of the fact that when we are designing and developing the product from the standpoint of usage, consumption, and safety, what exactly are those dangerous zones, the safe zones and optimum zones, and how do I manage my battery management system, my device, so that it always stays between the optimum and the safe zone max. And when it starts approaching the dangerous zone, there are automatic measures that can be taken in the device, which will ensure that the battery is, that the device is safe to use. So basically, what exactly happens in a thermal runaway is that inside a battery pack, there is one or two cells will move towards thermal runaway, and then it leads to a thermal propagation, and that thermal propagation basically impacts all the other battery and leads to a hazard. If we look at the kind of battery hazards that can happen, it is very important because to understand this, the nature of these hazards so that we can devise strategies to mitigate these things. So the three types of battery hazards that can happen is the mechanical stress, the electrical stress, and the thermal stress. So mechanical stress is when there is an impact, puncture, like the EV meeting with an accident and then the battery packs get damaged. Electrical stress like over discharging. If somebody wants to do a performance kind of a thing, they want to draw more power from the battery, that will lead to some amount of stress on the battery. and thermal stress, which is external heating or even internal self-heating. So all these events will lead to a kind of a hazard. Now, if the heat dissipation is better than the heat generation, you will have safety and vice versa. I think we talked about this, that thermal stress, little or no heat from a battery in operation. Electrical stress is over-discharging or overcharging of the battery, leading to a short circuit, and mechanical stress is impact or puncture. So what exactly are we doing? We are basically a chemical engineering, chemical science company, which makes some of the best known calorimeters for chemical products. And please make no mistake, batteries are a chemical reactor. There are two chemicals which are interacting, and the output is a current. So just like the principles of calorimetry, if we want to test the safety and the hazard profile of the battery, we need to use the same type of calorimetric principles of adiabatic. So the term adiabatic, which is, sounds very techy, nerdy, and geeky, it simply means that if there is a heat generation, a thermal event, then that thermal event is primarily limited or caused by the constituents of the battery which are generating that thing, which means there is no interaction with the ambience. So that all the heat, the thermal that is generated inside the battery remains. And that is the only way, scientifically, please mark my word, that is the only way you can test for thermal events in a battery. You cannot do it in a chamber. You can only do it under adiabatic conditions in an adiabatic calorimeter. So what we do is basically we try to simulate the worst case in a battery management system. So if a closed packed heat producing cells and the cooling system is failing, what it will do is that it will lead to a lot of heat production. And that heat production can lead to, depending upon how well the pack or the battery is designed and developed, a thermal runaway and a thermal propagation leading to an explosion. So this is basically the simple concept. Of course, there is a lot of complex engineering and math around it, but this is what exactly we are trying to do. So our calorimeter is a device in which we put the battery and we mimic the worst case scenario. In simple terms, we also call it destructive battery testing. Destructive battery testing means that when you put a sample battery inside the calorimeter, it will not come out alive, it will come out as a dead product. This is a destructive testing. There is another type of battery testing which is called performance or characterization testing. I talked about it last year, so I thought I'll change the topic slightly this year. I think again, please don't be daunted by this graph kind of thing. But what exactly what we are doing is that we are incrementally heating the cell. And as you can see in the yellow kind of zones, we incrementally over time heat the cells and see that there is no thermal runaway. The battery remains at that temperature. So for example, I started at a temperature of 40 degree, I heat it to 50 degree, battery remains at 50 degree. But then there comes a point at the time of heating where the battery runs into a thermal runaway. That is the adiabatic tracking mode. In that mode, you will see that now I am no longer heating the battery. The device is no longer heating the battery is getting self-heated. And then it leads to a point where the battery goes to extreme temperature of 320 degrees centigrade, and which will obviously lead to an explosion and fire. So what message we are getting is that, if I'm designing my device, my EV, my battery management system, where do I put the cutoff? And how do I know where to put the cutoff? Is it empirical? Experience? Because each battery is different. And when we loosely use the term lithium ion, within the lithium ion family, there are different chemistries available of the battery. The pack design as per EV is also different. The material used in making those packs is different. So how it is going to basically behave in the event of a hazard is going to be very, very different. And unless until we have studied this and taken steps to mitigate it, there is not going to be a chance that we can prevent this kind of hazard. So I'll just skip some of the parts. Just example of that, we can perform pouch cell, coin cell, prismatic cell, all kind of cells can be done through this. I'll take you to something more interesting. I hope the video works. Yeah. So this is a kind of mechanical stress testing, just a video for illustrations. When you see that the nail is penetrating into battery, and this is kind of desired or healthy scenario where there are only little fumes and no explosion, no fire. So in such a scenario, there is not going to be a major hazard. Oops. I think the next two videos are very interesting. I hope the organizers just bear with me. And I am indeed mindful of the time. Because as they say, seeing is believing. So we did mimic these kind of things in our own laboratory just to show and illustrate what exactly happens. So the second scenario is that when there is a fire, but it's a slow fire. And probably this could have been prevented by having some amount of heat dissipation strategies. And then the third scenario, which is the extreme hazard, is that when there is a mechanical stress, there is a big explosion. And that is the big explosion that we see in the newspapers happening on scooters, EVs, and those kind of things. I think we don't need to dwell on the details of that. But this is a scenario which will lead to extreme and very, very rapid propagation and hazard to the user as well as the device itself. So this is basically, the two type of products or calorimeters that we make, in which you can perform electrical stress, thermal stress, as well as the mechanical stress, that is nail penetration crash testing. We also have provisions for testing for the gases which come out, and those could be toxic. So in the third case, where there is a fire, extreme fire, that will also lead to a lot of toxic gases being produced. And if we want to analyze whether those toxic gases are going to be harmless, we have provisions for doing that also in this particular device. So I guess that's about it from